Professor Navid Asadi is an assistant professor at the ECE department of the University of Florida, who investigates novel technique for IC counterfeit detection and prevention, system and chip level decomposition and security assessment, anti-reverse engineering, 3D imaging, invasive and semi-invasive physical insurance, and supply chain security. He has received several Best Paper awards at IEEE International Symposium of Host, as well as ASME International Symposium of Flexible Automation. He is also winner of the Crow Innovation Award for University of Connecticut. He's a co-founder and also a program chair of IEEE Pain Conference, which, correct me if I'm wrong, is coming in a couple of months, right?
Correct, yeah.
Okay, so Navid, thank you for joining, and yeah, the floor is yours now.
Thank you. Thanks, Shivam. I appreciate it. Thanks, Avi. Thanks for putting together this workshop. I appreciate the opportunity to share our recent findings and talk about this topic, which is probably a little bit different than the other talks in this workshop. And I'm glad to share this area. When I was putting together the thoughts and the slides for this talk, there were two ways to look into this physical assurance and inspection and share with the audience. And one was doing a deep dive into some of the algorithms, neural nets, machine learning methods that are used right now. And the other was looking into the opportunities that are out there, which I believe, unfortunately, is still not getting enough attention. There are a number of groups here and there that are doing a fantastic job. I know in Nanyang University, there is a group that is working in Asia, Europe, but this problem is much bigger than basically addressing it in a smaller scale. The amount of the data which is required, the amount of the research which is required is, the more we are looking into this, we realize the importance and sensitivity of the area. So what you're going to see in this talk is basically a number of opportunities under different electronics, printed circuit boards, ICs, and the way that they are being physically inspected and assured, and how computer vision and machine learning, AI, deep learning can help us. So we won't go into those, but we get to see some of those problems that we really need help for the assurance. Governments are very interested about these methods. Industry is probably in the next level. Commercial industry is in the next level, but the amount of feedbacks that we are getting from people who we are working with on the project about the necessity of it is just a lot of ongoing projects in this area. All right, so I guess this audience really doesn't need me to go through this concept of the why security is a problem. I'm just going to probably skip it, but we all know this complex distribution and globalization of the supply chain is causing this. A lot of designs and fabrications, distribution, assembly, integration are happening in a lot of different parts of the world, and by the time we get them, before installing in a sensitive critical power implant or a military machine or a sensitive database, we need to be assured that the hardware is also as secure as the software. There has been a number of different counterfeits in the past, from recycled and remarked chips, all the way to the cloned and tampered chips. We have seen a good raise of awareness over the past, I would say, 5 to 10 years about the counterfeits on the scale of recycled and remarked, basically where we talk about some signs and defects on the package where there may be a scratch or there may be a ghost marking on a package which needs to be detected. And of course, when we're talking about tens of thousands or hundreds of thousands of chips, automation is required there. We talk about the methods that can fool, or some of the defects that can fool the machine learning algorithms that are developed for it. We're talking about 100% assurance. We can't let one chip go because that one may be the one that goes into a sensitive application. But recently, these two are getting a lot more attention. The cloned and tampered chips, a lot of short-term and long-term monetary benefits for an adversary in these two. And that had made it a big topic in these days in the conferences and in the other higher level programs that are coming out of different agencies and so on and so forth. A couple of examples that many of you should be familiar with. The big hack story came in 2018 on a Supermicro, regardless of whether it happened or not. Everybody in the community agreed that this is possible. And the boards, PCBs, by getting thousands of components on them, getting huge in the size, it's possible to add and tamper, modify part of the board and take advantage of it and have a hand on it later down the road when it's installed on a site. So, but physical inspection is not new. It has been around for many years, from the day with eyeball microscopes. Basically, human operators used to look into the boards, look into these capacitors and resistors and trying to extract the design, extracting the bill of the material and figuring out whether this is exactly what it was supposed to be in the design. Now automation is getting, new modalities are getting into it. We have seen the rise of use of laser, optical interferometers, and a lot of other modalities that are helping with identifying the components on a board, and also to some degree going into the third level, doing volume analysis with X-ray, terahertz, acoustic, and so on to be able to see these defects either unintentionally there or intentionally there. We have to make sure that we can extract everything abnormal. Okay, so we know, I actually removed, there was a slide about talking electrical inspection. We know electrical inspection is obviously there and a lot of progress there, but the level of complexity and resources and power and time that is required to do the test, especially on a huge system like PCBs, is just astronomical. So testing all single functionalities and verification of them practically sometimes may be impossible. And physical inspection by itself is not going to give 100% assurance, but it's going to narrow down the chance of the change or the malicious modifications that might have been in a PCB, or for that matter, any other systems, ICs or so on. So if you look into the market, if you look into the whole industry and global market, this imaging isn't just in semiconductors. There are a lot of other industries that are taking advantage of it with advancement of the computation, the deep learning and machine learning and all of these in medical domain, in mechanical engineering and material engineering. This area is growing really fast. We have in medical domain, the CT scan, MRI, now we have the doctors relying on the machine learning models to detect a patient's MRI or CT scan image, which a lot of times can be very difficult for a human to identify it. When we look into the battery industry and the reliability of the ICs and batteries, we have the same scenario. In mechanical engineering, one of the areas which is failure analysis, one of the areas which is really pushing the edge of imaging and trying to replace the models of failure and fatigue in the past with advanced imaging capabilities. So trying to come up with, it's a very amazing industry, trying to come up with new models and machines that can image the, for example, turbine blades and look into these tiny micron and sometimes sub-micron level cracks that can ground a jet fighter or that can ground a huge aircraft. So it's the porosity analysis on all of it. All goes down to how you collect these images and how you analyze them in larger scale. So the same concept is now in the electronics and electrical engineering with counterfeits, with complexity in the IC and PCB. We are looking into the same thing. Unfortunately, when I look at this area, because of the cost of it in electronics, we don't see a lot of contribution from academia. So we are lucky in our lab to have a good set of tools and machines, from desktop optical microscopes to 3D X-ray microscopy, FIBS and SEM, helium ion machines and photon emission, each of them perhaps $1 million and $2. So in total, we have about $10 million, but collecting the data basically requires such machines, right? So that's really one of the bottlenecks. We don't have, when we compare with other image analysis problems, we don't have a database like Facebook that people go and upload their face pictures there, and there is a free database right there for doing all the face recognition algorithms. For ICs, we don't have a PCB book or IC book, and regardless of all the proprietary challenge that will come in on the way. So there's a lot of challenge there, extracting these informations, annotating them, labeling them, and trying to, without intervention of these IPs and the proprietary of the companies that they have their information into the ICs, trying to improve these machine learning algorithms. We have started the effort though, and I'll talk about a little bit in some of the slides. And we are trying to put some of these data annotated on our website, trust-hub.org. So hopefully, and thankfully, it's picking up. I see people from different part of the world reaching out, trying to get access to the database, that we make it available for everyone. Of course, it's not the largest scale data at this point. When we talk about deep learning, we are really looking into hundreds of thousands or millions of images. We are not there yet, but that's really the goal where we want to be. Okay. So the rest of the talk, I'm going to now get into a little bit of more details of these problems. We will see these division of the talk into the ICs and the PCBs, and what are those problems that computer vision and machine learning can help in either destructive approach or a non-destructive approach. So let's first go with the ICs and destructive approach. I know time is limited. It's the last talk of the day, so I'll try to make it exciting and interesting. And let's probably skip some of the other modalities for it. But if you look into the destructive process, this is one of the costly processes for an IC. There is the ICs, someone designs it, it goes to a manufacturer, goes to a tester and integrator, and eventually it goes back to a facility that it has to be installed. So that end user or the entity that wants to install it needs to be assured the IC is what it has been designed. We know in particular Trojans, based on papers and the literature, there can be Trojans with 10 or 12 transistors among billions of transistors. So assuring that design is important. So this destructive approach is on the ICs is basically opening up the chip, getting rid of the package, going into the die, polishing the die down to the circuit level, and looking into the polys and the dopings and the connectivity of these transistors, gates, and from there, looking into possible Trojans. These Trojans can be change of the doping, for that matter. They can be a reroute. There can be a different gate installed or fabricated somewhere that it shouldn't be, replaced AND with an AND gate, or so on and so on. Looking into all these billions gates is not, used to be manual 20 years ago, used to be manual. The technique actually had a funny name, crawl around on the floor. They had all these papers on the floor and trying to look into the design and make sure that they are what they are supposed to be. So now it's not possible. It has to take advantage of the image analysis, image processing, and machine learning, and that's really these two steps from. So last speaker Danny, he was talking about even a step later from here. So extracting the functionality, getting a netlist, and then from netlist to be able to visually, or using graphs to visualize it, which is another required step to eventually look into the assurance, if that's the purpose of the use and the tool can be used. But going to there is a very costly process. Chemicals are involved in it, deep processing, material science is involved in it. And the whole reason that this part, or imaging or delayering, is complex is because our image analysis tools are not intelligent and smart enough to realize what a human or an operator realizes when looks at an SEM image. Okay, so if we have, and I'll show you some of the examples, if we have an image where the delayering has been done a little bit not perfect, and you have some residues left, or some silicon steel left, through the algorithms, they're going to come out as a defect, right? Whereas if a human could have looked at them, he would say, okay, this is the silicon, so I know there's a trace going from to here, and I can even see that under my SEM image. If we are looking into all these delayering steps, actually, this is one of the works that we did. We try to automate this whole process, and this automation of delayering is basically using the FIPSM machines. Windows of as large as 1 by 1 millimeter can be opened up with the plasma FIP. The process is still an open loop, so there is no feedback. The only input is the amount of the time or the exposure for the FIP, which is removing the material and tilting the stage back. So if you look at these two steps, one step, there are two columns. One is the FIP that removes the material. The other is the SEM, which collects the images, the sample. And this is an AMD 65 nanometer chip. I forgot the name of the chip, but this is a processor. And with the FIP, the material would be removed. It will tilt back, collect the images, and then again in another cycle, goes back in front of the FIP, material removed, and then image collected. Because there are some prior knowledge about the thickness of each of these layers, we can say, okay, FIP has to turn down for 100 nanoseconds or microseconds or more than that, okay? But if there was a way that the image could be automatically understood by the machine, this could be much more efficient. Collecting these images from an IC by a 1 by 1 centimeter area can take weeks or months. So let alone delayering them, collecting those images in one layer. So that's already a few weeks. You delayer it, go to the next layer, collect the images, another few weeks. So basically a 10, 12 layer IC imaging can take about a year. Some new microscopes are coming out with, instead of using one beam, using 60 or 90 different beams, make it faster, but they have their own challenge and the not enough energy for the beam, and another type of challenge that the machine learning algorithms and image processing will have when it gets to that step. So a quick example of how these images look like. At the bottom right, you see the raw images of these, and this is for a chip on a credit card. So I destroyed my credit card here, one of the old ones, and we tried to look into the circuit in it, going from the back side of the chip. So what you see here is the silicon, and then we have opened up these windows, which are here about 400 or 400 micron. And then this window at the bottom right is multiple layers. So as the FIPSEM imaging has been repeated in a loop, and you see as we go to middle, so it starts from the doping, then to the poly contacts, middle 1, 2, 3, all the way down. And as you go down, there are also some defects coming out. Those defects because of the redeposition of the beam itself back to the circuit. Sometimes the beam doesn't work as robust as it should, which is very normal for these tools, and a lot of challenge there. So eventually we get to some of these images. So this is an example of this image. At the top left, you see an image of middle layer 1. So there's noise there, there's middle lines, contacts, and every connection is important. If we can't extract and segment these traces in a way that, for example, this one is separate than this one, and an erosion or dilation is detected here, that's going to be a problem, right? So the noise of the SEM image is a big factor that has to be learned. And this is one way of how noise can come out. If you collect it with a test scan machine or a FEI machine or a Zeiss machine, the noise may be a little bit different. And there are a couple of models and in the machine learning world that learns the noise and tries to basically eliminate it from the images. As I said, it's still in its infancy. So a lot of good work starting, but comparing with where machine learning is in the design EDA tools, I think we are very behind. So another concept here that I would like to share is what you see here is a low KV image. So meaning the same chip, the same step as the IC is delayered. With a low KV, with your SCM, you can collect an image like this. Or if you increase the KV, which basically is the energy of electrons as they hit the sample, you can see a little bit of this too. So you still have your traces, you still have all of them, but you have the contacts as well, which are connecting the middle. So all these tungsten little circles that are connecting middle 1 to middle 2 are still shining up there. Your middle 2 is the subsurface, all these vertical lines. If this convolved image can be extracted in this layer with the algorithms, we are basically saving 2 steps of delayering, because in a low KV image, here is one set of information. There has to be one delayering step. Then we get the contacts, all these circles, another level of delayering, and then we collect the middle 2 layers. All right. So that's if all the features can be extracted from an image like this, then we are literally saving months or more than that, depending on the size of the chip. And by the way, we are not there yet. So the complexity and the noise and a lot of false positives are happening here. And another example of the low KV and high KV, and also other machines. So if you look at these images, this is actually from a helium ion imaging, and I'm just presenting how these different entities may use different microscopes to collect images. And if you look at this one compared to this one, helium ions having a better resolution. Features are actually, here it goes down to about 0.5 nanometer, but here we're looking into 2 or 3 nanometer of resolution. So the noise is better, everything is much sharper. and when you look at it, the features are a bit different, right? So if I train all my data on this, it is not as easy and as transformative to just apply that to these images. Some prefer to use helium ion for their imaging. So there are going to be needs for such problems in there. So I'm going to go quickly over a couple of tools that we have been working on to give you an idea of how the machine learning and image processing can help. We know over the chips, there are different areas with different density. We have areas like the AES and the processor where we have a lot of connections, and we have memories where we have a lot of repetition. We have probably capacitors and other components which are much larger. So for a microscope to understand how to collect these images and don't do an overkill of resolution where the features are larger, that needs a closed loop feedback. Thankfully, that foundation is in some of the microscopes, not all of them, but that brain or the engine that gives that comments to the microscope requires the analysis on the back end. So an ongoing work at our end, trying to reduce the time of imaging from months to weeks. And hopefully the ideal goal is actually to be able to do it even in a day. Concepts of compressed sensing are in there. And obviously the more data is collected, like any other method, the better we can improve the algorithms. However, there are unique challenges here too. So another quick example, I have to make sure I keep track of the time as well. So here we are looking into the contacts, and the goal here is, can we develop these algorithms for machine learning that extract the cells based on their contacts? So when we look into 14 nanometer or 28 nanometer node technology, whether it's TSMC or Samsung or Global Foundry or any other, there are specific patterns for the contacts. Not necessarily they are unique for per cell, per foundry or node technology, but they can narrow down the selections or the category of the cells that we are looking at. So for a tool that would understand the patterns of the contacts, will be very useful for understanding the final image. Another application, as I told you, when we are doing these delayering process, a lot of times stuff like this happens. So you have the silicon where it's removed, but it's not very uniformly removed. Some area have a little bit, so here which is darker, there is more silicon left, and we are talking about nanometer scale, right? Maybe here there is 5 nanometer silicon, there is 15 nanometer silicon left. But if this is passed through an algorithm to identify the contacts or others saying these are going to be challenged. So if I can improve my machine learning algorithms, then I don't have to go back to this whole SEM process and delayering and new chemicals recipes to make sure that they look as clean as what they have to be. And those, the two areas and directions are moving in parallel. Right? There is the sample preparation and the image analysis are really playing hand in hand in this area, and there's definitely need for the improvements. So the endpoint, we need data. We need the data. This data should be generated. We have started working on it. You see these images are from some of the chips from the traces, the doping, and hopefully when we have these data available, there can be a lot more work done in this area. And we are, as I mentioned, the trust-hub.org is a website that we are trying to put some of these data on. But another effort we are putting on is using the GAN to and add up and raise the number of the data that, in fact, we have a paper will be presented in the IEEE IPFA conference, which is also virtual, and my student will do the presentation in that conference. So this data is gonna include the different cells, their representation. And here you basically are seeing comparison of real images that we had in our data and the synthetic images. So this is really what we need to have in our database. When an SEM image is collected, depending on the stability of the beams are really good, but when it comes down to the contrast and the saturation and noise and reflection of electrons, things can be easily different. And especially when there are narrow edges and boundaries, there can be a lot of problems. So we are trying to use GAN to add up to our data. And that is, hopefully we can get to maybe hundreds of thousands or maybe millions of images in a scale of next few months. So I'm gonna probably go to the next topic, and I'm gonna skip the ICs, non-destructive. There are photon imaging. There are SMIM imaging, laser induced imaging. We have OBIRCH, we have OBIC, and all of them right now, the way the image analysis is done is by an operator, and that's what makes it expensive. Failure analysis requires it. Assurance needs it even more than failure analysis. But for the matter of time, I'll just skip all of those. Now let's look into the PCBs, non-destructive. I'm sure many of you may be aware of some of the works in this area. For board analysis, about 5-6 years ago, we started the work on using the X-ray imaging for extracting the traces and the vias of multiple layers of a PCB. With all the components, the capacitors, ICs, ports, inductors, and a lot of high Z material, X-ray gets very much attenuated. So when the X-ray is attenuated, because of the reconstruction process, we end up getting a lot of noise, okay? And that noise is brutal in evaluating and authenticating the board. Sometimes a lot of traces may be covered by this noise. And if that little trace or the via is the one that potentially is modified maliciously, no way to extract it. So many of these X-ray imaging algorithms and even the machines which are out there are coming from medical domain. Medical has been in X-ray at least half a century before X-ray came into the semiconductor industry. So a lot of algorithms are coming from there. A few new, by new, I mean maybe the past 5-10 years, we have quite a few techniques specifically for flat panel samples like PCBs, like laminography, where you try to move around the board in a way that you get around the noise or this attenuation that happens when a feature is under the shadow of a high Z sample, like a capacitor, that can create that noise. Okay, but still there is a lot more to be done there. The whole PCB assurance is a multiple step process. Different modalities again can play a role in it. From the optical images, when we look into the components on the board, so the Bloomberg big hack story, where the claim was there was an added component on between a memory and a processor, which gave the upper hand to adversary with something like optical analysis and a tool that would automatically extract the bill of material. That wouldn't be a problem. So that would have been detected. Under the imaging modalities, we have optical, X-ray, thermal, and even more can be. We can have cases where there is a capacitor. So we know capacitors are mostly in brown and resistors mostly in black, but there are a lot of edge cases where we have a brown resistor or a black capacitor. So the optical is not going to be really the way to give us, even we have a perfect algorithm, we are not going to be able to do it. So there is a need to go to the next layer of the modality. So something that can give us the material information. Or there was a nice work I remember last year from a group in Israel, and they looked into the illumination of the optical from these different components. And after looking into about a million samples, they realized that there is a correlation between that illumination on a resistor compared to a capacitor. So these are exciting novel ideas that we are really looking forward to see in this domain as well. But once these images are collected, we have the image processing, machine learning. There is a lot of process and clustering, neural network. I'm not going to even talk about how to extract the marking. I have a couple of students now working on it, and a ton of challenge where O can be seen as a 0, or if they are on a board, a via can be seen as a O, or for that matter, a 0. Nice problems to work on, and eventually the board, right? Extracting the traces and extracting the vias. A quick look at all the different parameters for modalities which can be used for PCBs. The most advanced ones, like the X-ray and even neutron imaging, all are giving us different type of images, and those images need to be correlated, sometimes fused with other images, because you don't necessarily get all the data from one image. You may need to combine it with another image and get information from another modality. Terahertz is one of the modalities that is not explored a lot because of its high frequency. There is a lot of information on the signal. Images can be reconstructed from the signal, and even material information can be extracted from it. So just giving an idea of some modalities here. So the ideal goal from X-ray imaging is something like this, to extract the connections all automatically. Looking into these connections, looking into the way they are connected to the components. There was also a claim in the BKI story where there were components between the layers, right? So on the traces, there can be some differences, and those modifications needs to be extracted. So lots of interesting problems to work on, and thankfully we have done some interesting work on this area. So here is a quick look at our most recent developments on optical. So I don't know if you guys can see when I zoom in this little corner of the board. So this is our most recent tool that we have used to try to just localize the components, the reference designators in the automated way. So we aren't really detecting what they are. We are just detecting where there is something. Whether it's a reference designators, which is basically a marking on a board that says what component is what, whether it is a pad where it doesn't have a component on it, right? Whether it is the pins of an IC. It has been shown that sometimes these pins may be missed. So the component is all good, but the pin may be missed or desoldered, or which can be a modification and eventually cause a problem. So this is just a very quick demo of it, and we hope that ideally the final tool that will come out of it can identify and extract everything on a board, regardless of what is the color of the board background. If it's green, now if it becomes black or red or white, then what's going to happen? If the logo is of a company changed today in something and they get bought by another company tomorrow, then what's going to happen? And all of those challenges from small to big, we're looking into this to address it as a whole. There has been some work about the PCB bill of material extraction in the literature, but I think the problem is a bit larger and bigger than what we see in the literature right now, because all aspects of it has to be explored. We are looking into 100% assurance. We are not going to be able to say, hey, I detected this capacitor, but instead of C12 as a reference designator or C11, it was C1. That one can be the modified version of it. So I don't know how I'm doing with time, but I'm assuming there's still some time left here, but I have a few more slides. This slide is a quick overview of the needs in the X-ray inspection for PCB. Each of these orange boxes, to me, are big problems. Acquisition of the image, reconstructing the X-ray images, creating a database, and eventually segmentation. Machine learning and neural networks are a key player in all of them. As I mentioned, a lot of these imaging tools and techniques are coming from the medical domain. So right now in UF, we are trying to build our own X-ray, and an X-ray which would be customized for PCB with the density of the components and their basically their location on the board, where you have some areas with a lot of dense components, some areas maybe sparse. There are going to be different needs during the X-ray imaging. Right now, the way X-ray images are collected is simply put a board on a system, spin it for 360 degrees, and then collect your images. That doesn't necessarily give all the good angles that image can be collected. So we are working on this. This is and by the way, there is a lot of interesting problems to work on here. I really encourage everyone to look into how these X-ray imaging can be better collected. And by the way, this step can get the input from the optical. So none of these are really independent. So if I do my optical inspection and I know what part of the board is dense and what part of it is sparse, I can use that information and give it to my X-ray tool, and then save time, and also give even some prior knowledge to how to collect the X-ray images from the dense domain and how to collect them from the sparse. So eventually we have the minimum noise or the attenuation from the high Z images. Reconstruction, everything is from medical domain. We don't have any. Recently, there are iterative reconstructions. Oil and gas industry and medical are there. If the acquisition step is different, is becoming different, the reconstruction has to be also different. So when you look into these 2D projections and you want to create a 3D volume from the 2D projection, the notion or understanding of 2D projections to help with building and creating the volume is the best tool to do it is deep learning. None of the algorithmic methods are going to be as good as the deep learning methods to do it. So then next step is going to be creating the database once we have it, and then eventually the segmentation. So our database for, I think I saw a question on, about the database. So right now we have our PCB database up. IC is still working on it. PCB optical is up. PCB X-ray hopefully will be up soon. trust-hub.org. And components are annotated. Anyone can take those, implement the different algorithms to look into the efficiency of those algorithms for the components. We are adding every month about 5 to 10 boards to this database. So we are going to keep working on it for the next year or so. I have my next two slides are a quick demo of the tools we are building for it. This one, we have a tool called S3A. Student Nathan is working on it. This basically gives you a good interface to help us with adding to the database, labeled components on the PCB. So the back end of it is this is a project that has a public and private part, so we can't release everything. But the public part of it, which is all using the algorithms which are available publicly, is available through the Trust Hub. You should be able. Feel free to email me. We'll connect you to be able to download it and collect the images and keep adding to the database or have your own. So the tool is semi-intelligent right now. So when you select on a part of a component, it will select automatically depending on your selected feature. It will detect, for example, the pins or the edge of a component or a marking or a trace on a reference designation on a board, and so on and so forth. So a good thing to play with. We are also doing the same for the X-ray domain. This is a longer one. I'm going to just skip it. So we have another interface where you can load up your X-ray images, and these X-ray images can be visualized in different layers. Different layers can be automatically detected, identified, and presented in one layer. So I'm not going to go over the algorithms behind them. And once we have those, the next steps are going through the annotation and segmentation. So this is, by the way, a very nice X-ray image. You don't get this type of X-rays when you have a board with a lot of components on it. The way it's collected is the traditional conventional tomography, but here you see a little bit of, so this part of it, you see how selecting a little piece. So right now here, the user is selecting a little piece of a feature of interest, and then the tool expands it to more areas of that feature. So in addition, there are specific algorithms behind it for identifying the vias. As you can see, there are these features that one can extract the via for it and do it in a semi-intelligent way. Okay. All right. I'm gonna skip this slide, and for the matter of time, so I just have 2 more slides. Basically, as I said, these modalities are adding up. We are really right now looking into maybe 2 or 3 of these. Each of these modalities are able to create an image, which that image can help with the assurance, or on the other side, they can be a tool or a means for an adversary to extract some assets. We talked about, I think the one talk before, or the 2 talks before the previous one, there was discussion of how to move the data around in a chip. So some of these modalities are providing the tools to look into the data traffic and visualize them. So if an attacker has some information about the chip and about the schematic and architecture at very high level, by some of the tools like optical probing or e-beam probing or SMIM, they will be able to track how data moves between one block with the other one. So if there are information, whether it's a key, whether it's a number of layers, whether it's weights or biases, some options or narrowing down some of these options, unfortunately, they can be extractable. So obfuscation methods should come in the design, as well as material-based solutions to basically hide these emissions that are coming and help an attacker to extract the information. So if you are interested more about this material, we had a book published in this year, Physical Assurance for Electronics, Devices and Systems. I'm also teaching a class at UF, which has an online part as well. It's probably still for UF students, but we're trying to expand it further. We have a YouTube channel as well. Probably if you put in physical assurance and inspection of electronics on YouTube, you should be able to find that, where we have short videos by students describing their projects, how they're working and what type of problem they're working on. And then last slide, a shameless plug in for the IEEE Paint. So as Shivam said, it's coming in a couple of months. Where this conference, the call for paper is closed. We have interesting papers, interesting keynotes. So this conference will be only about physical assurance, and hopefully will help the community. And with that, lastly, I want to thank the team. Obviously, all of these works none of them would be possible without the team, a combination of engineers and postdocs, PhDs, a lot of help from master students and undergrads who help us with the annotations and implementations of algorithms. If we want to have PhD students work on it, it would take a long time to do these works, but thankfully a large team that's working nicely together and enabling the progress in this area. So with that, I don't know how much I'm over time, but thanks for your attention, and I'm open to take any questions.
Thanks, Navid.
Such excellent talk.
Thank you.
So, Navid, I see one question from the audience in the Q&A, which says, what is the budget you typically need to build your own X-ray system for PCB inspection?
Couple of $1 million. So depending on, I know, and so we are obviously working with government, right? And we're trying to go after funding to build the machine. There are a number of programs here in US that helps. I know in Europe there are different programs, and always there are smart ideas. I think a couple of years ago at Paint, so our photon emission machine is about $1.5 million-ish. But there was this student from one of the universities, Germany. They had their own system put up together with about hundreds of thousands. So putting a detector, a source, and staying away from a lot of unnecessary items. Like some of the machines have this very expensive stabilizing table or other features. But if the purpose is specific for something unique, it can be there can be costs saved. But unfortunately, it's expensive. I think that's really one of the problems in this area, which we should, I guess, as academic and people in this domain, we should promote it to help with bringing in funding to this area, because in the industry world, they are always working with the commercial tools available already out there. I used to work with Zeiss and Tescan, and as long as there is a big customer in another domain, oil and gas, let's say, or medical, it's going to be very difficult to work with. But governments are a bit more open to this right now. But we are looking something between perhaps $1 to maybe $2.5 million.
And like from technical challenges, is it something which is like you know how to make it, or still there are like technical challenges, even if you have the funding then?
Oh yes, absolutely. So right now working with 3 companies, one who provides the source, one who provides the stage, the one who provides the cabin. A lot of challenges there. So usually would be a 2-year project if things go well. But the most challenging part is going to be how to reconstruct the images, because the way we are going to collect the images is different than the standard ways. But there are also a lot of open source tools, so that's why we are getting help with a lot of students. So crowdsourcing to figure out what is out there, can it be used for partially even for what we will be developing, or this area for if needs that. There are going to be challenges, but we are certain that what is out there right now is not the best for PCB imaging. We have been working in this area for like 6 years, 7 years right now. And no matter how advanced is the deep learning, there is a need for all these machine learnings eventually. But if your real feature is hidden behind your noise, you don't want to predict it. For the assurance, you want to make sure you see those features and then detect them. You don't want to just predict and guess, oh, okay, because there is some noise on this trace, then most probably this is the one connected. That seems a doable approach, but we have to have a proof that the trace, at least some areas are clear under the noise. And from there, the post-processing algorithms will take over.
I just want to add that part of the problem is not just the equipment, which is extremely expensive, but to find the right manpower, because these people are also very attractive to the industry. So whenever we are finding the right people, so the industry gives them a much higher salaries, and then we need to retrain people from scratch. So you need to be very lucky to find a group of people that work with you at least 5 years in order to know how to do it in the right way.
Absolutely. I'm actually letting one student graduate a year earlier because he already got an offer much higher than my salary. So so that's why having starting early is important. So that's why we try to like start with in my class. I have both undergrad and grad students, and thankfully they are actually showing a lot of interest in this area. So when it's working with the equipment, looking into images, application of machine learning, they learn the machine learning side of it as well as the equipment side of it. So I totally agree, 100%. It's very difficult to keep them, the good manpower and everything. That's a challenge, yes, totally.
Navid, I also have a couple of questions on your talk, actually. So, first thing, like you mentioned often about the speed at which we can acquire the data, the images, right? It could be from days to months, depending on what kind of technique we're doing. There are also many companies which are doing this as a service. Of course, there are only a handful of them. So, like, is this speed also applies to them, or like this is only in the research or the academia, since we are doing it in a manual manner, or let's say with a certain sets of tools, or like are they able to automate it to do it faster?
Sure. So it's a speed and also the number of chips that you want to sacrifice, especially when we are talking about Trojans and assurance. You don't want to look into one layer on one chip and another layer on the other chip. Everything should be on one chip, right? So some of these companies, the way they work, they sacrifice like hundreds of chips and then prepare every chip for one layer. So that speeds up a little bit. But if you want to do everything on one chip, it's going to be a little bit slower. As far as I know, the challenges are still there. I know a couple of companies like Technion in Canada and a couple more in Europe. And we reached out to some of them. And when we were trying to actually get a quote, besides the cost, which was very expensive to reverse engineer what old node technology, it's say 135 nanometer or 90 nanometer. The time range we got was about 6 months to 1 year, and depends on what you want, right? If you want the full analysis, but the principle and the way that work is being done is same. It's about the manpower. Sometimes if you are doing it, we want to do it fully automatic, right? So a lot of the stuff are not fully automatic right now. With more manpower on it, it can be also faster. If you put 10 machines, it can be also faster, but it won't be on one chip. So that doing the stuff on one chip limits the time a little bit.
Thanks. Also, I was checking, for example, if we see Danny's talk and also your talk, I think one thing which is like a common comment from both that, okay, we have deep learning, which works very well in image classification, and like it is quite strong. The problem in this domain is that there is not enough data to actually train upon, right? So there have been many challenges with this in other domains, or let's say subdomains of security. For example, even in side channel, and it has started to move faster when like open competitions are being organized, especially in the flagship conferences. So I mean, do you think like this could be the way this can work? Of course, there is a hindrance of having that kind of equipment in different groups and all. But do you have any insight on that, or maybe a plan to do some conference, maybe like Pain or something?
So we actually had a plan to do a competition at Pain last year, but moving the stuff into virtual got a lot of time from us last year. Didn't get to it. But you hit the hammer. It's about the equipment. Unfortunately, security. I mean, people in the material science, they have access to this equipment, but people in the security, they are not yet having their hands on these equipment. And sponsors or governments, they haven't yet put that. I think things are changing in US a lot right now, and I see it, but if you don't have the equipment, it's going to be difficult. So that was our incentive to try to put the data on TrustUp, because even when you have the data, there's a lot of challenge. So our hope is to put the data and get the help from the community. On PCB, it's picking up nicely. On IC, it's going to be challenging. But if anyone, usually for academic people, they can go to the material science department and usually borrow or book a time and do these tests. But the sample prep process should be there, and the delayering process should be there. The whole package should be there. If we have some competition, I guess it would be best to be more on those testing the algorithms rather than creating the images, because without the equipment, or like GAN methods that can help with creating, there is also a lot of value there with some sort of data. The model that, so one of the cool things that can happen, there is a ton of SEM images in biology domain, in medical domain. The noise is the same noise. But when it is on semiconductors, the way that the beam is creating the image and causing the noise is the same as if it is on a biology sample. So if we can learn that noise from those samples and apply it on these semiconductors, perhaps there can be stuff that we can learn from there. We are working on such stuff as well. But you're absolutely right. There are challenges and definitely help needed from the community.
Also, I think like there is a skepticism in sharing resources. I think in the VLSI community in general compared to the software. I think that adds to it a little bit.
Agreed. Yeah, agreed.
Unfortunately, we need to generate more Trojan horses so people will understand that this is a real problem. Similar to what the antivirus people did, they just separate viruses so people will buy their equipment. No, I'm joking. No.
Yeah, unfortunately, I mean, something catastrophic should happen.
Yeah, the problem is that people said, yes, everybody talk about how the Trojan horses, but they are not real threat. There's no famous case that people found how the Trojan horse that at least people know that it causes damages.
Agreed. Yeah, unfortunately, they're kept in a closed environment. I mean, I can just share that when Bloomberg news came out, our office phone kept ringing for a month. Do you have a technology ready right now that we can buy it from you? So people, the ones who are directly involved, they know the problem is real, but it has its own politics around it as well. But we were actually just getting the request. Is it available? That's actually, I don't know if you guys saw the spin-off from a couple of faculties with Mark Tiranipur and another faculty from Ohio State University, and there are four of us. We spin off a little startup trying to commercialize some of these tools so that they become available for those who need it. But there is also a lot of work there. So the need is there. If someone gets into this area, they'll see that the need is there, the market is there. But unfortunately, in academic environment, where is the most innovation, there is not enough support to get people involved at this point. But I know Singapore, they are doing actually a lot of work. Dr. His group, I know his group, the work that they do and so on. Compared to EDA and design tools, it's not there yet for sure.
Right. So thanks a lot, Navid, for sharing all this interesting details and like really a good landscape of what's there, what's the problem, and what direction should we go to. So I